It's a great pleasure to introduce our first Bhaumik lecture. This is from the Manny L. Bhaumik Institute that's hosting it. And Nima has been a leader in theoretical particle physics for 20 years. He exploded on the scene with large extra dimensions and has been going strong ever since then. He's currently a professor at the IAS at Princeton. He's won numerous awards. There's the Gribov Medal, the Fundamental Physics Prize, the Sackler Prize, the Gambarini Fellowships, and for advisory board, the Bhaumik Institute Advisory Board. And a fact that I think many of you know is that he's a movie star. So he will sign autographs. And without further ado,
all right, it's really a tremendous pleasure and honor to be giving the inaugural Bhaumik lecture. I've come to know and meet times. He's really an extraordinarily wonderful person. He has a lot of vision, of course, for his own life, vision for science. He's very sensitive about what's going on in fundamental physics, and he cares about it very, very deeply. I think rather sophisticated understanding of what's going on, what our goals and ambitions are, and could be. And the reason I chose this title for the talk is that there's one question that comes up over and over again whenever we get together with Manny. He keeps asking us, whatever is going on, whatever wonderful, cool thing is going on in our developing understanding of quantum field theory and string theory and so on, he always asks us, so is this getting us closer to unification? He truly and passionately cares about unification. And so it's a very interesting question, because our notion of what unification is, what it should be, what we might expect it to be, hope for it to be, has evolved over the years. And so that's really what I wanted to talk about today, is in this spirit, what's going on with our quest for unification in fundamental physics. Partially a status report, partially some, towards the end, some wild speculations for what might be coming in the future. But anyway, dedicated to Manny for making this wonderful new institute here possible. So I was told that this is it's meant to be at a level of a colloquium, a mixed audience, so there's some experts here in the audience, so well, hopefully there'll be something here for everyone. So just a very brief reminder of what it is that the sense in which unification has been the central driving theme in the development of fundamental physics for around 400 years. This is the main amazing thing that we started learning with Ming, that the same force of gravity that pulls the apple down to the Earth keeps the moon going around the Earth. Later, we discovered that these ancient things like electricity and magnetism are actually different facets of exactly the same phenomenon. And every time in the past that we've understood that seemingly unrelated things are actually different aspects of the same thing, we have found yet third things, other things that didn't have anything to do with the first two, that end up being related as well. In this case, after we saw that electricity and magnetism are different aspects of the same thing, we understood that light, which doesn't seem to have anything to do with thunderbolts and whether rocks repel or attract each other, has to do with undulations of electric and magnetic waves. But the journey towards unification really accelerated into deeper and more uncharted and more interesting territory in the 20th century with the discoveries of relativity and quantum mechanics. So relativity told us that time and space can somehow be mixed with each other and are different aspects of space-time. And that's something that had many other consequences. The undulations of space-time are associated with gravity, and it made it possible to articulate ideas that were impossible to articulate in the Newtonian worldview. For example, that the universe can expand. The universe can expand because it's this dynamical entity. As the universe expands, more and more space is generated per unit time. It's not that it's expanding to a pre-existing something. It's the very dynamism of it allows us to talk about something like the expanding universe. Similarly, quantum mechanics changed everything about physics. We lost the classical notion of determinism, but we gained something. We found out that particles and waves, which seem like very different phenomena, turns out to be different aspects of one thing, not always particles. There's no waves fundamentally, but particles that move according to the laws of quantum mechanics. So these were the two big revolutions of the first 30 years of the 20th century. And much of the rest of the 20th century was about putting these two giant principles together and figuring out how to talk about physics in a language that's compatible with both ideas at the same time. The general theoretical structure that allows us to do that is known as quantum field theory. It's time for the 20th century to figure out both theoretically, how quantum field theory works, and also find a specific instantiation of a quantum field theory, the famous standard model of particle physics that describes everything we know about the elementary particles so far. I think the bigger, more interesting lesson, these two principles told us that the long enough distances is essentially inevitable. Let me see if I can put this up here. Is that better? Okay. In other words, if you just handed a group of theoretical physicists, you give enough food and water and graduate students, laws of relativity and quantum mechanics, they would eventually figure out that the gross properties of the world at long just today. Something that you're probably all familiar with is that the interactions that we know of are associated with these little stick figures. Electrons is ultimately associated with the interaction when two electrons and a photon come together at a point in space-time. The gravitational interaction associated with the electron is two electrons and a graviton meeting at a point in space-time. And the more exotic, less familiar interactions that we discovered in the later, things like the strong and the weak nuclear forces, are ultimately, when we go to high energies, short enough distance, are associated with the same kinds of fundamental interactions. Quarks interacting with gluons, electrons and neutrinos interacting with U and Z particles, and so on. I raise it one more time. I don't mind yelling, but and everything else that happens in nature is a concatenation of these things over again. So these basic interactions take place over and over again and give rise to the dizzying array of phenomena that we see in the world around us. That fact that that's what things boil down to, as I'll stress again in a second, is a basic consequence of relativity and quantum mechanics and almost nothing else. Now, we have a particular view of these particles and interactions that we've seen in nature. We won't go through this in any detail. That we have these interactions, and we have these kind of interactions that I alluded to. It's a menu of an interesting degree. It's not the most complicated thing you could possibly imagine, not by far. It's not the simplest possible thing you could imagine. For instance, there are the familiar particles like electrons and maybe the up and down quarks that you've heard of, but there's 3 generations of these guys. There are 3 of them. There could have been 93. Could have been 1. Okay, so it's a kind of intermediate level of complexity. Now, let me at least make the logical claim about this business about the structure of the universe being inevitable. In a different talk, I would spend longer actually explaining this as possible to explain with a degree of honesty. The claim is that whatever the underlying ultimate theory is, if it's, I mean, it is possible to explain it honestly in a different setting completely, but I mean in a setting like this, it's possible to explain it relatively honestly. Whatever the ultimate theory is, if it's compatible with the principles of quantum mechanics, it's guaranteed that at long enough distances, the interactions that we see will be dominated by the basic interactions of 3 things coming together at a point. Not 12 things coming together, but 3. So the simplest possible interaction will actually dominate what all the interactions that we see are. And also interestingly, we know that in quantum mechanics, particles can have spin that come in multiples of a half times Planck's constant. But and in principle, you could have particles of spin 13,001 halves. But what we find is that the only possible consistent interacting particles that you could have to take very simple values. They can have spin 0, a half, 1, 3 halves, and 2. And that's it. And in fact, there can only be one of these guys that's spin 2, and that's the graviton. So, but that's something that you can figure out without thinking about falling elevators and apples and things like that. It's really sort of pure thought. Once you know the basic principles of relativity and quantum mechanics, you find out you have one of these guys that makes things go around in orbits and so on. But it's one of the possibilities. The 3 halves guy is interesting. You can have at most 8 of them. Okay? And they have very prescribed kinds of interactions that's associated with the idea of supersymmetry I'll say a little bit about later. You can have some number of these spin 1 particles, some number of a spin a half, and so on. Their interactions are very special. You can have any number of the spin 0 that you want. But that's it. There's an incredibly tiny menu of possibilities, all associated with these elementary 3-particle processes. And everything boils down to what is the precise menu, what are the particles, and what are the strengths of the interactions. And that's it. Out of the continuous infinity of possibilities you could imagine, everything has boiled down to making these decisions. So already here, before we talk about anything else, fancier things, unification, string theory, all sorts of other stuff, this is a very profound sort of unification. Because we're finally describing everything that we know about in nature in one coherent language, with using one coherent set of ideas and structures. Now, there is a little bit of fine print to the story that I just told you, because all of this incredibly constrained form of the interactions makes an assumption that all the particles that are involved in those have 0 mass. Why would you make such an approximation? Well, we've learned over the last 100 years that the basic simplicity of the laws of nature is apparent when you go to very, very high energies or very, very short distances, which needs very, very high energies because of Heisenberg's uncertainty principle. So you would think that in some good 0th order approximation to the physics, what it might look like at incredibly microscopic scales, you should be able to ignore all the masses of the particles. And that's true, except for an important caveat, that particles that have a spin are discontinuously different between when they're massless and massive. Massive spin 1 particle has 3 degrees of freedom, because you can always go to a frame where it's at rest and see it spinning and tilt your head and see that it's spinning in many other directions. But a massless spin 1 particle, you can never catch up with it because it's moving at the speed of light. You can never tilt your head to see it spinning in other directions. And so a massless spin 1 particle has 2 degrees of freedom. This is a discontinuous difference between massless and massive. You can't be a little bit massive just like you can't be a little bit pregnant. Okay? So there's this one extra guy, and so this is a challenge because the particles that we see aren't massless, they're massive. We know they have to have this ridiculously constrained set of interactions when we go to incredibly high energies, and therefore, somehow those degrees of freedom that we see in the massive particles have to rearrange and reassemble into these legally interacting degrees of freedom that we just talked about for the massless particles. And before July 4th, 2012, all the particles that we knew about in the standard model of particle physics did not allow us to do that. And we needed something else. We needed something more. That something more, if you went back to the menu of possibilities, you asked, what have we seen nature do? The reason I put some of these things in red and black is that we had seen particles of spin a half, 1, and 2 is the graviton. We hadn't seen particles of spin 0, haven't seen particles of spin 3 half. So it's possible that, that these options were realized by nature to solve some of our puzzles. And indeed, the Higgs particle, which was famously discovered on July 4th, 2012, was exactly what was needed. A single dinky extra degree of freedom that allowed all the massive particles that we know and all the degrees of freedom to smoothly reassemble, continuously smoothly reassemble and interpolate into high energy, legally interacting massless degrees of freedom. So on the one hand, this tells you why the Higgs is exciting. It's the first really new elementary particle that we've seen in decades. Okay? And on the other hand, it shows there's something that's still left, something we haven't yet seen nature do compatible with its general principles, which is to exploit the possibility of having, in some approximation, massless particles of spin 3 halves. That's associated with this famous idea of supersymmetry that we'll talk about a little bit more in a moment. So that's a rough summary of where we are so far. Now, some of the central dramas of the 21st century that we'll then view through the lens of unification through the rest of the talk are that these 2 giant principles that give us all of these things, the ideas of space-time and quantum mechanics, are likely to be approximate. We have many reasons to suspect that those ideas are approximate. Certainly, space-time is almost certainly approximate. It's even conceivable that we have to deal with limitations of quantum mechanics when it comes to talking about applying quantum mechanics to the entire universe of cosmology. And then there are questions closer to home. We don't understand the answer to very simple things like why the universe is large with large things in it. We can do many other things. We can predict the magnetic moment of the electron to 12 decimal places. But very easy, simple questions like this a kid could ask, we don't give good answers to. Just very, very briefly reviewing what these problems are. One of them has to do with very simple thought experiments. If you try to look at a smaller and smaller region of space, you need higher and higher energies because of Heisenberg's uncertainty principle. And in a world without gravity, there's no difficulty doing that forever, looking at sharper and sharper resolution at shorter and shorter distances. But in a world with gravity, eventually, something very bad happens because you put so much energy into such a tiny region of space that you're trying to look at that you collapse that region into a black hole. And that makes it impossible to extract the information you were trying to get. Okay? That's a very simple thought experiment that tells you that the notion of space and time can't be precisely measured, can't be made precise sense of when you get down to incredibly tiny distances at around this famous Planck length of around 10 to the minus 33 centimeters, the tininess of which reflects the incredible weakness of gravity compared to all the other interactions that we know of. So that's the doom of space-time problem, which you can explain in 45 seconds. The other question of why the universe is big, you can also explain easily. We know it's a very basic fact about quantum mechanics that even lowest energy configurations, even the vacuum, has energy. The size of the vacuum energy is related to the typical frequency of oscillations of whatever system you're talking about. But if you ask about fluctuations in a box of empty space, as you make the box smaller and smaller, the wavelengths are getting smaller and smaller, the frequencies are getting higher and higher, and the amount of quantum mechanical energy should diverge. It should be infinitely large. If you make a very simple estimate for how large it can be, well, you can't make the box smaller than the scale where space and time break down. But if you just put it there, it would give you an energy density of the vacuum, which is around a Planck energy per Planck volume. And that would make the universe curve nearer the Planck scale. So it would be 10 to the minus 33 centimeters big, or explosively doubling in size every 10 to the minus 43 seconds, in rather violent disagreement with this nice, big, comfortable 10 billion year old universe that we see. This universe would suck. Okay? And it's radically different than ours. So this is good questions in physics have this character. They're not technical questions of what happens in the 17th decimal place of some esoteric calculation no one cares about. They're about things you can explain to anybody, simple facts about the world. And here there are. There are two incredibly simple things that go to the very heart of our understanding of the principles of space-time on the one hand, and these simple issues about why there is a macroscopic universe. All right. So this is an outline now for now viewing some of these challenges and also talking about things in a somewhat broader context through this lens of our progress towards understanding unification. So I want to talk about a number of different aspects of unification, roughly ordered. I'm going to start with what I call the Ming vase version of unification. Okay? This is sort of a canonical picture if you're reading popular science books in the 1970s or the 1980s. This is the picture you might have for the kind of unification that we're after. That we have these different shards of bits and pieces of the underlying laws of nature, and we're looking for this one beautiful object that takes these broken pieces and glues them together. The symmetry is broken, something like that. They glues them together into some spectacular, larger thing that we didn't know about. Okay, so that's this Ming vase view of unification. This is a view that was very popular. It was talked about a lot in the 70s and 80s. It's a view that the majority of working theoretical physicists have abandoned today. Okay, and part of what I want to do is explain why they've abandoned it, and explain what might be. Thank you. I didn't ask for that, but that's very nice of you. But explain why it might be, from some point of view, a retreat, why we feel we're forced into this retreat, and what has replaced it. Because part of the reason for the excitement in many parts of theoretical physics is that we feel that it's been replaced by deeper things, more unanticipated, stranger, more exciting, more profound things than we had thought before. Okay? And in fact, I want to then move on to tell you why, for very general reasons having to do with the existence of gravity and quantum mechanics, there was something wrong with this picture all along. That this whole idea of reductionism, that we're supposed to understand, go to shorter and shorter and shorter distances and find what's going on at the ultimately tiniest zero distance, whatever that means, that was fundamentally a flawed idea from day one in a world that has gravity. Okay? And that has interesting consequences. So the part two is going to be some sort of general comments that, even if you didn't have a specific theory in mind, like string theory, some general comments that would lead you to suspect that the Ming vase picture couldn't be completely correct. And some general things about more surprising unifications between gravity and the other interactions that do come up when you start thinking about these things. Part three, I will talk about what's perhaps the most profound recent thing which has happened on the 20-year time scale of a very surprising unification between the theory of ordinary forces, gauge theories, quarks and gluons, and gravity. And there are very surprising hints of deep interconnections between these two ideas from a number of different points of view. And so that's an example of a hidden unification that's not of the Ming vase variety, but it's something that has many people very excited, including the people who are here. One aspect of it is being actively studied at the meeting, which is being run here at the Bhaumik Institute right now. From here, I'm going to move on to the final two topics, which get gradually more wilder and more speculative, but where at least I feel that hidden unifications are going to come from. One thing which I'm personally fairly confident of, although probably not many other people's confidence will be much lower than mine, is that we're going to see that the ideas of space-time and quantum mechanics are actually unified with each other. That it's not like there is a quantum mechanical system that generates space-time somehow, or certainly not the other way around, but that we'll come to see quantum mechanics and space-time as different aspects of one more abstract object whose principles we don't know, but we'll start to understand. The most speculative set of things that I'll tell you is about one step further, which is a kind of a unification between the notion of an observer and of a system. And this is something whose teeth ultimately shows up in cosmology, and I'll spend a few minutes talking about that. The very last thing that I'll say here will give some hope back again, and this is more reflecting my own psychology than anything else, back to the Ming vase view of unification, although interpreted in a very different way. And after that height of speculation, I want to spend, if I have time, a few minutes talking about prospects for learning more about these things from experiments. Okay? So this is something incredibly important. Physics is still an experimental subject. It's more and more difficult to do experiments, which is why it's more and more important for people to push for making them happen. Okay? And so I want to tell you what some of the prospects are for getting experimental information about these things. All right. So let's get going. So first, this Ming vase view of unification that I already told you about. The earliest instantiation of this is looking at that table of those funny quantum numbers of the various particles in the standard model of particle physics. There are three colors. There are these other interactions, it's sort of the weak interactions and electromagnetism. We have quarks, we have leptons. And this is this little slightly complicated table that I told you about. And fundamentally, there are three strengths of interactions for the color and the electroweak, the electromagnetism and the weak parts of this story for those stick figure interactions. And something that was noticed by physicists in the early 1970s is one of those things that must have, to the people who discovered it, seemed like a miracle that dropped out of heaven, is that this somewhat complicated table actually looks like it almost perfectly glues into something bigger, just like that Ming vase. Okay? So that if we imagined that three colors of gluons that are rotated into each other by the strong interactions and two associated with the weak interactions take electrons and neutrinos and rotate them into each other and so on, that there could be a larger symmetry that rotated 5 of those labels into each other. Okay? And if you just posited that and had some fairly simple things that could be rotated into each other in that way, that could explain this somewhat complicated pattern. And even more amazingly, if you just imagined that there are essentially 10 kinds of labels that were being acted on, that all of this complicated set of stuff could just come from an incredibly simple, technically speaking, incredibly simple representation of a larger symmetry, the SO10 grand unified symmetry. This also wasn't just aesthetics, because it made a prediction that there shouldn't be 3 independent strengths of the interactions. At ultra high, where finally this Ming vase is put back together, you should see that the strengths of these interactions are equal to each other. And that allows you, by the rules of quantum field theory, to make a prediction, what physics is supposed to be about, for what the values of those parameters are at low energies. Okay? And that prediction, roughly speaking, in the mid-70s worked out. So this is absolutely spectacular. It also predicted things that the proton should decay in 10 to the 30 years, which didn't happen. Okay? So the simplest versions of this idea were also ruled out. because they made predictions. Okay? All right, but there are more interesting versions that survive that I'll say a little bit about. Now, there's one step we can take beyond that, which is quite a bit more radical and more interesting. That's this famous picture where you imagine taking little points, particles, and replacing with loops of string. Okay, so that's something almost all of you have heard about, unless you've been in a cave for the last 40 years. The idea is that we might imagine that all the elementary particles are little loops of string. The size of the strings would be around 10 to the minus 31 centimeters. And doing that has one immediate remarkable consequence, which is that if you imagine ordinary particles interacting, they're little point particles, then when they hit each other, there's something singular happening there. And that's why we get to associate an arbitrary interaction strength, because we don't know exactly what's going on there. So we have to put a little fudge factor. We don't know precisely the strength of the interaction. But when you draw the analogous picture with loops of string, that doesn't happen. There's no special point where they hit in this way. It's a nice, smooth picture. And that means that if there was a theory of strings, if it made sense, it couldn't contain any adjustable parameters. So that's a big leap from the thing that we talked about a second ago, where you went from 3 parameters to 1, or it's more than 3. This is that just conceptually there are no free parameters at all. Right? Now, this triggered an enormous amount of excitement for good reasons, amongst others that the gravity is an inevitable part of this subject. It's not obvious that once you say there are little loops of strings that the gravity's got to be included, but gravity had to be included. I think most of us think this is the most striking and deepest indication for this Ming vase idea of unification you could possibly imagine. That indeed, when you get to incredibly high energy short distances, everything is made out of the same stuff, just these little vibrating strings. We're lucky to have one of the people who invented this subject in the back row there, Michael Green, and I'm sure that he and all of his friends were ridiculously excited when this general possibility occurred to them, and also, of course, triggered the interest of an ocean of talent in theoretical physics for many, many years. But the first reason to be excited was that it gave a conceptual reason, a possibility of having a theory with no adjustable parameters whatsoever. The fact that it spat out a basic structure roughly of the kind of laws that we could see was a wonderful additional bonus. All right, so now there's many other ingredients that come along when you have string theory. You can even talk about many of these things without string theory. Remember I told you the possibility of having the particle of spin 3 halves forces, if nature is to exploit that idea, it needs to have this notion of supersymmetry. It has to double the world in the same way there's particles and antiparticles. Every ordinary particle would have to have a partner whose spin differed from the ordinary one by half. And here again, another quantitative amazing thing happens. That I told you that if you imagine the strengths of the interactions are identical, whether they're related by string theory at very high energies or for some other reason, even if we go back to these more conventional pictures of grand unification, if the strengths are equal up there, then we can calculate precisely what the strengths have got to be at accessible energies where we do our experiments. And if you do this extrapolation with all the particles that we know so far, you get an answer that's wrong by quite a bit. But if you assume that nature exploits this idea of supersymmetry and extrapolate everything down, now saying that there are superpartners around as well, down to energies that we're about to probe and are probing now at the Large Hadron Collider, you find the following picture. We can say it backwards. You measure the strengths of the couplings at low energies. This is plotted as the inverse. You can't read it. So this is the electromagnetic weak and strong force. And then as you run it to very high energies, you find the 3 of them just converge to a point with just astonishing accuracy. Okay? This didn't have to happen. 3 lines don't have to come together at a point. Okay? Not only that, they didn't have to come together at a point at an energy scale that's within an order of magnitude of where grand unification and string theory and general pictures about putting quantum mechanics and gravity together would suggest that it happens. This is something that just falls in your lap. Sometimes you know that you're on the right track in this business when things happen easily. Einstein struggled for 50 years, 40 years to try to unify gravity and electromagnetism. These people who ran into this just diddled around with a few equations. They knew a little bit about group theory, and it all just happened. Okay? So this is often an indication that you're on the right track. Now, so this is a picture that was, these couplings were measured precisely enough to be able to draw this conclusion in the early 1990s. And that's why in the early 1990s there was a collective, almost 100% belief, maybe not quite, but a very clear belief in most of the theoretical physics community that when the LHC turned on, we would be flooded with superpartners. We would see supersymmetry. And so this picture remains valid, but we haven't seen any of them yet. So there's something wrong. 30 years of speculation about these ideas. This is the best thing we have going for them still. And we haven't seen the smoking gun that really should have shown up. In fact, this is sometimes said like everyone expected supersymmetry to be found at the LHC. We haven't seen it, and now people are nervous and worried about it. But in fact, it's not like that. Anyone who looked at these things with any knowledge or sensitivity back to the mid-1990s or late 90s knew there was something a little bit wrong. These things could have shown up 20 years ago. The fact they haven't shown up now is like the 11th and a half hour for them not showing up. So we're in a strange sense of tension. You have these things going for it big time, then you have the direct looking for them, having them not show up. Okay? So this is one of the sources of tension about our feeling about unification. Now, given the time, I think I won't go through this in much detail, but I just want to say that my own best feeling, my own best bet about what's going on, which I've believed for a little over 10 years now, is that there is a variant of this simplest supersymmetric picture, which is what's going on. In this variant, you only see half of these partner particles at accessible energies. And I just want to say that this is an example. In this picture, all of these successes about the unification of couplings, all those things go through unchanged. Other little niggling problems with the idea go away. But the picture, by its internal logic, does not necessarily predict that you should see the particles at the LHC. In sort of half of the parameter space you would, and half you wouldn't. So roughly speaking, the partner particles of things like photons and gluons would be accessible at LHC energies, but all the remaining particles would be much, much heavier. And there are various pictures for why those partner particles of gluons and photons and W and Z particles should be at accessible energies that have to do with dark matter. But details about how the dark matter could work out could give you a spectrum of particles that's either accessible or inaccessible at the LHC. Something that, when I was thinking about this talk, I went back and dug up when we were really systematically talking about these things back in 2006. We said it. You know, there's I won't go through it in detail, but this is paraphrasing. There are two pictures of what the dark matter could be. In one picture, things are accessible at the LHC, and the other one, they're not. So it's no desire to not be ruled out or something like that. It's already something we were saying almost exactly a little over 10 years ago. This picture did make a prediction, though. It makes a prediction for the mass of the Higgs particle. And it predicted that the Higgs particles should come out between roughly 120 and 135 times the mass of the proton. And it came out around 125. Okay, so it's it's not a very sharp prediction, but it's a relatively narrow range. So that's at least a mild check that has been passed. Now, that might not seem like very high standards to you, but this is one of the very few ideas which has not been killed by the Large Hadron Collider so far. Okay, in fact, it's been slightly strengthened by the fact that at least this prediction checks out. Okay, so that means that we don't necessarily have to throw out this amazing picture of the couplings unifying. There are ideas that existed for a decade already that suggested there could be variants of this basic picture, even if we don't see the particles at the LHC. Okay, but there's a more distressing reason to be not as enamored of this Ming base picture. And that's a realization that was made within string theory itself, although it has antecedents in all kinds of other parts of physics before, that despite the fact that it's a theory with no adjustable parameters, it has a gargantuan number of solutions. Okay, there are different possible, what look like approximate vacuum solutions, what could look like worlds, one underlying set of equations, a single underlying set of equations, but which could produce an enormous number of possible long-distance universes. Now, often this notion of a multiverse is thought of as a philosophical thing. Here it's not quite as philosophical because these universes are in principle connected to each other by physical processes that could allow you to go from one to the other. So it's not this Leibnizian picture of these just philosophical universes. It has some teeth. You could in principle do experiments that would make little bubbles of some of these other places, even though it could be very, very hard to do so. But on top of that is something more speculative, that all of these bubbles are actually realized out there somewhere, cosmologically, and that there are so many of them, an enormous number of them, 10 to the 1,000 of them, and most of these regions in this humongous multiverse are actually lethal. There could be nothing there. And in a tiny, minuscule fraction of places, the conditions can be right for structure to form, you and I to be sitting here to have this conversation. And in this picture, that the properties of the particles and forces that we see and the precise value of all the interaction strengths and so on are reflecting a deep feature of the underlying theory. They could be reflecting a kind of a random accident of which pocket in this gigantic multiverse we ended up in. So it's ironic that starting with the most unified structure that we've ever seen in physics, the idea of string theory, which allows us to in principle calculate what all the strengths of these interactions and the particle species, everything can look like. That's what's giving us the strongest evidence internally, theoretically, that we've seen that the precise particles and their patterns and things that we see are not fundamental. Okay? So I think this is, when I said that most people have abandoned the Ming vase picture, this is a big reason for it. At least from the structure of the theory itself, it's not what it seems to want to do. So I would say that picture, that popular picture from the 70s and 80s, is likely dead, if this picture is right. Okay, so now let's talk about why this is not such a bad thing. And it's not such a bad thing because part of the underlying philosophy that simplicity shows when you go to higher and higher energies, shorter and shorter distances, we have reason to be suspicious of. So the idea that the fundamental physics is defined at incredibly high energies is something that's likely wrong. One aspect of this we've talked about already. It's that when you do incredibly high energy experiments, at some point, you no longer probe shorter and shorter distances. You make black holes. The black holes grow larger and larger and larger. Okay, so very high energies start turning to very large distances again. So it can't be that the fundamental things at incredibly high energy and that longer distance things emerge from it, like tables and other things like that we're familiar with in everyday life. When there's gravity and quantum mechanics involved in this way, incredibly short high energies start corresponding to incredibly long distances. There's no natural home for the ultimate end of the reductionist mode, just for this very simple reason. This actually has lots of consequences elsewhere. There are interesting gravitational constraints from the consistency of large black holes on very low energy physics. For example, you might very naively think if you have a box that you can count the number of degrees of freedom that you could have in that box. Maybe you have a little spin-a-half particle, and in every little lattice site in the box, you can either decide if it's up or down. So you would naively think that the total size of the space of possibilities is exponential on the volume of the box. But that's wrong. If you try to excite many of these degrees of freedom at the same time, they'll have so much energy they'll collapse the box into a black hole. And in fact, the largest number of degrees of freedom that you could put in the box doesn't scale like the exponential of the volume of the box, the exponential of the area of the walls of the box in units of Planck's graphic bound. There are other interesting indications of gravitational constraints on not on very, very high energy physics, but in principle on very long distance physics. For instance, there's an obvious fact in the real world that we talked about already. Gravity is much weaker than all the other forces. But in your mind's eye as a theoretical physicist, you might imagine making the strength of gravity much, much stronger. Okay? Why couldn't it be that the electric force was way weaker than gravity? If you're a naive, long-distance quantum field theorist, nothing wrong. In fact, it seems better and better. You make the strength smaller and smaller. It's easier and easier to calculate. Why not? Why can't we treat gravity and the other forces from each other? Okay? But it turns out that there are lots of indications of deep consistency issues that arise with black holes that tell you that gravity should always be the weakest force. And if you try to make other things much weaker than gravity, important facts about black holes, how they radiate, the notions of entropy associated with them, and so on, will start to go haywire. In fact, this makes rather specific predictions for what happens when you take two black holes that have the largest amount of charge that they can have for a given mass. That's such that if you balance them, there would be no force between them. So this idea that gravity should be the weakest force makes a very specific prediction for what the subleading effects that come in for the relative, for the strength of the interaction between these particles. It means that it should always be such that in the end they repel a little bit. That makes very specific predictions or corrections to Einstein's equations. And you can check whether those predictions are true or not in string theory. And in every example that we've studied, they're true. But it's an example of something that you can infer just general consistency conditions of the existence of very large macroscopic black objects at very high energy, which also gives you a general lesson. Another deep feature of unification: gravity and the other forces can't be treated in isolation from each other. Okay? This has nothing to do, apparently, with a very specific underlying model, just the simple fact of the existence of gravity suggests these things. There are other indications of a deep sort of unification. For example, we have an expanding universe, but we don't understand, as the universe expands, it's not like it's expanding into something. As I said, it's like space is stretching. But that means there's more degrees of freedom later in the universe than earlier in the universe. Okay? Where do those degrees of freedom come from? We don't know. Okay? So somehow, there are degrees of freedom that start off life incredibly ultraviolet, very, very high energy. Much higher energy than the Planck length. We don't know how to think about them. And yet, as the universe expands, they turn into good old-fashioned ordinary degrees of freedom in our large world. Where do degrees of freedom come from in an expanding universe? Again, we don't know, but it's clear that long and short distance degrees of freedom in cosmology are the same. What we see is the hugest, largest things out there cosmologically today had their origin in the highest energy things that we could probe early in the history of the universe. It's also amusing from many of you, the global history of cosmology looks very symmetrical between the past and the future. There's a picture where you start with a big bang. There's a period of acceleration. We think that that's inflation. There's a sort of ordinary cosmology period. We're accelerating again today. That's the famous fact that the universe is accelerating. And the most likely fate of any of us is that we're going to tunnel out into some region with negative energy and experience a big crunch. So it's fascinating that the whole cosmological picture of the world is very symmetrical between the past and the future. These ultraviolet degrees of freedom here turn into infrared degrees of freedom and return back into ultraviolet degrees of freedom as you head towards the big crunch. So this is, I think, an absolutely fascinating and qualitative indication for a sort of much more interesting than this Ming vase, right? It's not like you take this thing and that thing and you glue them together into a bigger thing. It's that things that seem to have absolutely nothing to do with each other seem to have a deep reason for being related. Okay, so now let me move to the most now let me move to the most some of the most concrete and sharp and most exciting things that are going on in our understanding of unification, and that's the unification between gauge theory and gravity. Now, in fact, there are two indications. A very simple one that anyone could have thought of at any point. Another more sophisticated one that string theory suggested very early in its development, that gauge theory and gravity should be related to each other. So the dumb one is the following. If you think of a photon or a gluon or something, it's a particle of spin 1. A graviton is spin 2. So why can't you think of a graviton as a bound state of two gluons, right? So that's a great idea, that the graviton is a bound state of two gluons. Oh, there's a little problem with that. Gluons are, photons are pretty weakly interacting. They're sick going that way. They would go that way, and then you're in big trouble, right? So they don't look like an effective particle of 2. nonetheless, that's some early indication. You could think, oh, there might be some relation between gluons and gravitons. More interesting was the condition in string theory that particles like gluons and photons were associated with a little open-ended string, while particles like gravitons were associated with closed loops of string. And now you could draw an almost equally dumb-looking picture that you say here's a little closed loop of string, but couldn't you think of it as a little open loop that went from here from there, and then another one that went back from there to there? Okay, so you could take a closed string and think of it as being made up out of two open strings. That's from that picture. Now, this picture actually works in a very precise quantitative way. In fact, the best way to understand and do concrete calculations for how strings interact with each other when they're strings is to think of them in precisely this way. Okay, so here's there's a slogan: the closed is like open, or like gravity is like gluon squared. Now, this was a wonderful thing that was learned by the string theorists in the late mid-late 1980s. But this general idea has had an explosive renaissance in the past 10 years or so. And it seems to be a rather deep, again, and a hidden kind of unification between fundamental interactions that at the moment, it's certainly related to the things that were seen in string theory before, but can be phrased as a completely general fact about the way gravity and theory of gravity and gluons are related to each other. There's this remarkable relation between gravity and gluons. I think the best and sharpest form of it was articulated by Zvi and J.J. Carrasco and Henrik Johansson right here almost 8 years ago, I guess. And in a very precise sense, you can think, if you imagine a bunch of gravitons are coming in and bang into each other and going back out, you can almost think of it like the gravitons going together, okay? And in a quite precise sense, if you knew the amplitude for how the gluons interact with each other, there's a way of squaring it to get the answer for the amplitude for how the gravitons interact with each other. This entire workshop meeting here this week is devoted to this interesting topic. What I find about it is it's completely general, and it's something that could have been, in principle, discovered decades ago. Okay, it could have been discovered in the 1960s, 1970s. It could have been discovered at any point all this time, but it was laying under our noses for all this time. What does it take to find it? You have to look at the world through this lens, that there's things remaining to be understood in the structure of the good old-fashioned theories that we know for a fact describe the world, that they have subterranean connections between each other, not this cookie cutter, take this piece and that piece and glue them together and we'll make something prettier, but in a sort of more profound, deeper sense, that they're not they have to be combined into something bigger, but that they're actually different aspects of the same thing. Or that there's dictionaries that convert questions you ask in one theory to questions you ask in another theory. So that's this newer kind of unification that has replaced, I think, in the mind of a lot of practicing theoretical physicists, the thirst for the unification of the level of making predictions for the value of the coupling constants and all the rest of that stuff. That doesn't seem to be going anywhere at the moment. But this is going somewhere, and so people are spending a lot of time thinking about it. Now, there's another aspect of this gravity open, closed is open squared, that has dominated the thinking of many theoretical physicists for the last 20 years or so. And it's not that I talked about. In order to motivate it, I want to go back to some big lessons that we learned from quantum mechanics. So quantum mechanics told us in just thinking about discovering physics, there are two very big lessons. One is that it was important to pay very careful attention to what perfectly precise observables are. If you just talked in a fuzzy way, imagine you're someone who's sort of futzing around trying to discover quantum mechanics. Somewhere in the middle, 19 teens or something, you might have the idea of phase space is a little bit fuzzy. You have the ideas of like Bohr-Sommerfeld quantization and so on. But you can have this kind of fuzzy idea. There's some sort of fuzzification of what's going on. There's an X and P at the same time. It kind of sucks, right? It looks like you've sort of lost something, that there isn't going to be anything very, very precise. But it pays even if it looks like you're losing things, to try to think what you do know precisely. Because what you can know precisely is what a theory should be about. Okay, so that's the first sort of 0th order philosophical lesson. And the second thing that we learned with quantum mechanics is that disappointments can turn into triumphs in an interesting way, and it's related to unification. You see, you can have a drastic loss in the kind of observables you have, and that's what people suffered in the discovery of quantum mechanics, right? That's why people like Lorentz were so disappointed that you lost the deterministic picture of the world. There are vastly, vastly fewer kind of observations you could meaningfully talk about. You can only talk about probabilities in the end, okay? But it had a silver lining. The fact that there's many fewer observables means that what's left has to be, the things that are left have to be related to each other more closely than they were before, simply because there's less you can talk about, okay? Because there's less you can talk about, the things that are left have got to be related to each other in a more surprising and interesting way. And that's quite literally what happened with quantum mechanics. That very indeterminacy that so depressed Lorentz and his friends is what allows waves and particles to do the same thing. Okay, so that's an example. You lose observables, what's left is more united in an interesting way. Okay, so now, if we pursue this program of thinking about what the precise observables are, the first thing we have to do is ask what it is that quantum mechanics asks to do when we make observations. And it's a very simple thing that we emphasize to, at least one aspect we emphasize to students of quantum mechanics. The predictions of quantum mechanics are probabilistic, and therefore to make them you have to do the experiment infinitely often, right? Because it's, in order to get a very precise prediction, you have to do the experiment infinitely often. So that's one infinity. There's another infinity that you need that we emphasize a little bit less often, is that you have to do the experiment with an infinitely large measuring apparatus. Okay? Because if not, the apparatus itself will have quantum mechanical fluctuations. So precise predictions in quantum mechanics asks you to drag around an infinite apparatus with you everywhere you go that records the results of all the observations on finite systems, and you have to do that over and over again an infinite number of times. Okay? Gravity changes the story in an important way, because if you try to do this in a fixed size room, in this room, right, I try to make any measurement in this room, I'm obstructed from at least one of those two infinities, because I can't make the apparatus infinitely big. Why? Because as I make it bigger and bigger, it inevitably gets heavier and heavier. And before it gets infinitely big, it gets so heavy that it collapses the whole room into a black hole. Okay? And why is that bad? Well, because then I have a finite amount of time before I get sucked into the singularity and die, so I can't do the experiment over and over again. Okay? So it sounds like a totally ridiculous thing. Practically speaking, this is utterly to the infinity, no, not literally, utterly to the 100 irrelevant, whatever that means, okay? It's not of any practical significance, but we learned in quantum mechanics it's very important to keep track of what the precise observables are, and this tells you there are simply no precise observables in some interior region of space and time. Where are the observables? The only kind of observables that you can have is when you take the apparatus and you take everything and you move them off to infinity. Okay, so you can precisely talk about questions where you throw particles in from infinity, you have them bang into each other, they come back out to infinity. You can certainly do that, because you can make the apparatuses arbitrarily large and separate them and so on. But those are the only sort of things that we can talk about. Okay? So that's yet another drastic reduction in the number of observables. We went from classical to quantum. That's the worst, right? We didn't have determinism. But now, even within quantum, if you add gravity, there's no observables in finite regions of space and time. The only precise observables we can talk about go out to bounds, go out to infinity. Okay, well, probably the biggest conceptual revolution in this field in the last 20 years is the realization that not only do the observables, do the experiments start and end at infinity, that might lead you to suspect that if the experiments start and end not in the interior of the space but at infinity, maybe there's a description of what the physics is where you never have to talk about the interior at all. Okay? And that's something that's been made very precise in the context of the really only system we can imagine that puts gravity in a box where the interior of this box is, has the geometry of an anti-de Sitter space. And this is really our sort of first baby example where we can think about some of these is like space emerging out of degrees of freedom that don't have it, gravity, even strings, all of these features of the physics on the interior end up being, so a quantum gravitational theory in the interior of this anti-de Sitter space ends up being, amazingly, completely equivalent to a good old-fashioned non-gravitational theory, ordinary quarks and gluons, but when they're incredibly strongly interacting with each other. Okay? So when these guys are very, very, very strongly interacting with each other. So you can't, remember, one of the problems with making two gluons the same as a graviton is that if they're weakly interacting with each other, nothing forces them to stay this way. They could go that way, they could separate, they could do all sorts of crap. But if the interactions between them are incredibly strong, then you can quickly lose track of the individual particles involved. Okay? And if you have any process involving these very strongly interacting quarks and gluons, then they end up being entirely equivalent to weakly interacting gravitons and strings and so on, but not in the original space with interaction. So at a sort of cartoon level, this is another aspect of this closed equals open squared kind of dictionary. But this is very precise and complete, and it's a kind of an astonishing hidden unity. And it's really completely changed the way people think about what even the goal is, a quantum theory of gravity. But I have to say that there's an interesting tension here, because this picture that ordinary quantum theories, ordinary quantum field theories are equivalent to a theory of gravity in anti-de Sitter space, give you one view of what quantum gravity is about. And this is a view that's, on the one hand, is incredibly unified, exposes this hidden unity. There are different aspects of the same thing. On the other hand, it would lead you to suspect that any quantum theory you imagine, roughly speaking, would be equivalent to some kind of gravitational theory that lives in anti-de Sitter space. So from the point of view of whether there's sort of one underlying theory, this idea of string theory, that there's no adjustable parameters, all the different things that we see are different solutions of one underlying beast. If you just had this picture, you would never dream that. Okay? It would not remotely be obvious to you that something like that is true. On the other hand, what was learned a few years earlier than this, in the 1990s, is that string theory was even more unified than people realized in the 80s. There does seem to be one underlying set of equations, and this gargantuan set of possibilities that is so depressing for the Ming vase picture of the world is nonetheless solutions of one underlying thing. So how can these two things be true at the same time? How can it be true that, that any quantum theory is equivalent to some gravitational theory in ADS, while there is this picture in anti-de Sitter space, but in flat space, which seems to be ultra unified? That's, I think, a deep question we don't know the answer to, and it's not clear the timescale for making progress on this question. But I don't think we're going to have. I don't think that people are going to be satisfied until this basic tension between these points of view is resolved. All right, so that's an internal theoretical reason to not be satisfied with this state of affairs. There's also an environmental reason not to be satisfied with this state of affairs, which is that our universe looks nothing like anti-de Sitter space. Okay, it's a perfectly good toy model. It's a perfectly good box. Physicists like putting things in boxes so you can study them. But there's a big difference between this box world and our world. Our world has cosmology. Our world had time. It evolved. And that's not the case in this toy model. In particular, the notion of time did not emerge. The notion of time is exactly the same in the interior of the box as it is on the walls of the box. Whereas we have a universe that had a Big Bang in its past. Even more confusingly, it's accelerating today. The fact that it's accelerating today means that what we see out there is fundamentally finite. It's huge, but it's fundamentally finite. And that fundamental finiteness is a big problem for quantum mechanics. Because remember, quantum mechanics asks you to drag this infinitely large apparatus around with you everywhere you go to make precise statements about anything. And that infinity is even in principle not possible in the kind of cosmology that we appear to have. So in my mind, I think to many people's mind, this is the sort of deepest conceptual paradox, set of paradoxes that we're dealing with. And it's very likely, I'll need to understand not just emergent space, but emergent space and time, and perhaps even extensions of quantum mechanics to help us make sense of how to apply quantum mechanics to the entire universe. Not stupid things like it's violated in a lab when people do simple experiments, but when quantum mechanics seems to cry uncle when applied in these cosmological settings. All right, so don't worry, I'm not going to, we're not halfway through, okay? So, but I do want to just say a few more words about the remaining topics are somewhat more speculative, but I do want to say a little bit about them before concluding. Okay, so where we've gotten to is that there are hidden relationships between ordinary theories that we know describe the world. There's hidden relationships between gravity and gauge theories. Aspects of that hidden relationship that I've talked about. There's indications that the space-time has got to be emergent. And up to this point, there's something which is winning, okay? Especially with the last set of things that I talked about. The most precise understanding we have of what quantum mechanics and gravity look like in the interior of this box is in terms of a good old-fashioned standard quantum mechanical theory that lives on the walls. Okay, so something that's very intensely being explored by people right now is how this works in detail, trying to understand what the mechanics is for how this actually happens. But the sort of basic slogan is that quantum mechanics is king, and other things are slaves to it. So, you know, the space emerges, other things emerge out of it. And that's a great slogan for progress for a while, but my own suspicion is that it can't be the final story, and we're going to have two more steps, and that's what I want to speculate about in the remaining time. So this is, as I said, what people are very actively exploring for very good reasons, trying to understand the mechanics of how correspondence between quantum field theory and quantum gravity works. But that quantum mechanics is king, and space emerges from it. But as I've indicated, we need more. We need to probably understand emergent space and time. Once time is emergent, it's not even clear what quantum mechanics means. So it seems much this is the speculation. There's some other underlying structure out of which quantum mechanics and space-time will somehow emerge inexorably. They're not sort of two separate things that we have to learn in the picture from the early part of the 20th century. We have to learn how to describe them in the language of quantum field theory, putting them together. Now we're trying to imagine how in the details, perhaps, of the entanglement of the quantum states and these strongly interacting systems, geometry emerges from that. But that makes a relationship between them asymmetrical. The idea here is that there are some underlying objects out of which they emerge together. They sort of had to both be there at the same time and joined inexorably. Now, there are various circumstantial reasons why you might expect something like this to be true. There are some, somewhat slightly esoteric and technical reasons, but are very well known to quantum field theorists. It's a peculiarity that our understanding of quantum field theory is never happy in 3 dimensions of space and 1 of time. Okay? The textbook understanding of quantum field theory is in Euclidean space. Okay, so you really imagine there's 4 dimensions of space and 0 of time, and you define what it's supposed to be in Minkowski space by an analytic continuation. Okay? So that's quite interesting, because the place where it's perfectly well defined, the objects that you calculate do not have the interpretations of anything causal, obviously. They have the interpretation of anything probably amplitude. You're calculating amplitudes, phases. There's no eyes. Okay? It's only the analytic continuation to Minkowski space that at the same time gives you time and turns these things into objects that have an interpretation of amplitude. Okay? So the causal and probabilistic quantum mechanical interpretation emerge simultaneously together. That's one indication of causality and quantum mechanics being closely tied. Okay? There are other more recent versions of this, which I won't have time to talk about, where there are different kinds of mathematical structures that seem to underlie at least certain aspects of quantum field theories in 3 dimensions of space, in Minkowski space, that don't start from Euclidean space, but kind of start from the other end, the most relativistic possible space you could have with 2 spaces and 2 times. Okay? That's also something that has no canonical interpretation. But there are natural objects that you talk about there, and only their continuation to Minkowski space endows them with an interpretation in terms of quantum mechanical processes. Okay? Other circumstantial clues is that while special relativity, space-time, and quantum mechanics seem to sort of be in vague tension in front of the scenes, behind the scenes they buttress each other. Okay? It's relativity that makes it impossible to simulate quantum mechanics by stupid hidden models, as much as large collections of people continue trying to do this dumb thing to this day. Okay? And on the other hand, it's quantum mechanics that makes it almost impossible for the symmetries of Minkowski space to be accidental, emergent, long-distance things. Okay? It's, if you take a wave on a rope, it's governed by the wave equation, which has a Lorentz invariance. But there is an ether, the rope, sitting there, right? So it's easy to get, in many situations, things that look relativistic, even though it's accidental. That was, after all, how we discovered relativity, by building an ether. Okay? That's how Maxwell got Maxwell's equations. Incredibly hard to do that when you have quantum mechanics. And that's because quantum mechanical fluctuations port the knowledge about the breaking of Lorentz invariance from very short distances to all distance scales. Okay? And it's incredibly difficult to arrange that the speeds of light of all elementary particles should be the same, even though we experimentally know they're the same to 15 decimal places. Right? So they have a little bit of tension in front of the scenes, but they're very friendly behind the scenes. One makes the other more rigid. Okay, well, there are other aspects of this, which I don't have time to talk about in detail, but there are a number of qualitative indications that these two concepts are more closely related to each other than appears at first sight. Now, something else that people like Zvi and his friends pioneered was another thing which is sitting there in the structure of good old-fashioned theories that we know and love. If you try to just make calculations for what happens when you bang gluons into each other and see what comes out, 2 gluons go in, 3 gluons go out. This is a slide stolen from Zvi. You need to do calculations like this to make predictions for experimentals with the Large Hadron Collider. If you do these calculations, you find these horrendous, horrible 25 pages of algebra that look like this. And that's what you get if you just follow the usual rules that Feynman told you for how to think about what these scattering processes are, with particles coming together and hitting each other at points in space and time. Okay? And there's no a priori reason to expect that the answer is simple, because you're asking a complicated question. So complicated questions often have complicated answers. But people needed to do these calculations. And morally good behavior is often rewarded in physics. And they found incredible, ridiculous simplicity. Okay? So these hundreds of pages of algebra collapse to these ridiculously simple expressions. I don't need to tell you what these things are. They're roughly the sort of square roots of the momenta of the particles. But this already tells you that the standard way of thinking about what space-time and quantum mechanics are, and it's what made Feynman famous, is to figure out how to describe the scattering of particles in a way that makes these two principles manifest at the same time by drawing pictures of particle trajectories in space-time and summing over all the ways it could happen to make quantum mechanics manifest. You can do that, but it's hiding something. It's hiding some other structures. And that it pays to try to figure out, it might pay to try to figure out what those structures are. All right, well, that's something that many of us have been trying to do now for a number of years. Depending on our count, this activity has been going on for 40 years if you start with Roger Penrose, or 20 years or 10 years, but there's many avatars of this kind of program. But the general idea is, and what's nice about it is that you can turn it into a very precise question that you can try to make progress on, is to take this subclass of questions involving the scattering of particles, very physical questions, even things that we measure at accelerators. You take the subclass of questions and you ask, is there some other question to which those functions are the answer? Okay? Is there some other set of principles? Is there some other objects that determine what they are, instead of the usual picture of imagining through space and time with things banging into each other? Okay? If you can do this, then you might start getting an indication for what some different starting point is, from which you can then deduce that there was some interior space and time, with the particles moving around and hitting each other and moving according to the laws of quantum mechanics. And the nice thing about it is it's not philosophy. You can't bullshit. You either get the right answer or you don't for these questions. You can check whether you're right or wrong. And you have a very sort of specific thing that you're looking for. Now, this has been going on, as I said, for quite a while, but it's starting to converge, and at least in an interesting subset of theories, to some formulation of completely standard ordinary physics again, where we can start to see this idea that quantum mechanics do actually emerge in a very concrete, very precise way for these questions from more elementary, simple building blocks. What's been the most interesting to me in this process is the contact it makes with beautiful new structures in mathematics, structures that are even new to the mathematicians who have been thinking about these things for entirely different reasons for the past 10 years or so. And the kinds of mathematics that show up are so primitive and simple. They're combinatorics. There's simple shapes generalizing triangles and plane polygons and things like that. Just slight, small generalizations of those ideas are in quite startling ways related to this very basic and simple physics. And I won't explain this in any detail, but just to say that I won't tell you anything about what this is, but there's a specific sense that if you want to know the answer for the amplitude for this process of 8 gluons, 2 in, 6 out at the LHC, that these ideas tell you that to do that, you have to draw a shape in some completely auxiliary space. This is not in space-time, it's just in some abstract space. And the volume of that shape gives you the answer. Okay? And the geometry of this shape encodes in an interesting way, in a not very hidden way, but certainly in a very novel way, the ordinary physics of the locality of interactions in space-time and quantum mechanical unitarity. Okay? So I think this is a concrete example. It's a baby example, a small step, but it's a concrete example of this idea that we'll see space-time and quantum mechanics as actually different aspects of the same thing. In this story, at least, they cannot be separated from each other in any way. There's one thing, there's one object, and both things emerge simultaneously in a way that connects to those circumstantial reasons I told you they might be connected early on. All right, well, I've gone over time, so that's probably a good thing. So I don't tell you how the observer and the system are to be made, are to be unified with each other. I guess all I'll say about it, maybe I'll just read this slide, is that we've said this a number of times already, but quantum mechanics falls into two parts, the infinite observers and the finite systems. And this is possible approximately for everything that we care about, but conceptually, it becomes difficult when you have gravity, and that's why we have to go out to the boundaries of space-time. And when we have cosmology, at least especially our accelerating universes, or when we go back to the Big Bang, it's not just, there's nowhere we can go. We just seem to just run out, okay? Now, this sounds bad, right? Now we don't have anything that we could, talk about anymore. If we take this philosophy from quantum mechanics, where we should pay attention to what the precise things are, we seem to run out entirely. So I think the only thing that's left is that there should be something wrong with this separation. And that the silver lining behind this will be that this seeming distinction between what a system is and what an observer is has to be somehow removed in a more complete understanding of the physics. I'll just give you this is a pure, okay? So I won't go through this, some extra things that are what are bad about it. But a pure fantasy is something like this. Perhaps finite systems, a new kind of kinematics associated with them we don't know about yet. And they have new observables, whatever that means. It's not our standard notion of observable right now. Now, describing this is going to be as difficult as trying to describe someone in 1870 what the world would look like after we had Hilbert space, or in 1910, they might know that X and P are fuzzy, but they don't know about what precise things are coming next. 1910, like polled people, they would say, oh, things are going to be terrible, right? Everything looks a little bit, or maybe 1915, everything looks somewhat probabilistic, it's going to be messy. They wouldn't know there's something precise coming next. Well, I'm fantasizing that perhaps there is something precise coming next, that there is a way, there is a new kind of kinematics, new notion of observables that makes sense for finite systems, and that what we think of as standard quantum mechanics arises in a limit where the number of degrees actually, but where those infinite number of degrees of freedom are split into a big infinite part, which is the observer, and a small infinite part, which is the system. And if something like this is possible, it could be that the multiple dual views of physics we now have are artifacts of this split. Okay? Again, very, very roughly, you might imagine there's like a real equation like this. There's some z squared plus y squared plus minus x squared is epsilon squared. So there's sort of one thing that we see there. There's one unified hyperboloid. But if we take a limit where epsilon goes to 0, it seems to consist of two disconnected pieces. If you just saw one piece or the other piece, they would look like, well, there's this, there's that. You could imagine it's much more complicated. It's a much higher dimensional equation. And yet, really, it's because we've taken a somewhat artificial limit of something which is more smooth. It's a pure cartoon. But already something that we can try to do in seeing whether anything like this is right by trying to understand more deeply, theoretically, where these mysterious dualities that we've seen between gauge theories, gravity, other dualities, where they come from. But bringing it back to this question, I think this even rough picture raises, to me, an interesting possibility that we've been greatly misinterpreting this string landscape. That we're not supposed to imagine that we have all these different solutions and they're all different. They're all different, they're all realized somewhere out there in the universe, that they're all different pieces of something and we're in one of them. In other words, we have a picture now that we're supposed to use the word and. There's our vacuum and the other vacuum and the other vacuum and all the other possibilities, and we have to find some way of figuring out why we got ours. It could be that the world is or, and that all of these different possibilities are actually correspond to different ways of taking one big object and giving it a system/observer interpretation. So it's sort of slicing the same thing in many different ways, roughly speaking, corresponding to the different horns that you could think of in that previous cartoon. So that would be interesting. That would be interesting because it would obviate a lot of the questions that we're asking. In that the reasons we threw away the Ming vase is that we thought there are zillions of different possibilities. In this picture, there could still be many different possibilities, but they wouldn't be, in a sense, distinct. They would all be, different ways of writing one thing and, roughly speaking, like expanding one object in different bases. Which would mean that if you knew everything about, you see, the reason it brings the Ming vase back is it puts back to the front our own vacuum we possibly can. Because it might be needed more. Okay, whereas if the word was and they're all disjoint, then we wouldn't be able to do that. Now, for all the reasons that I told you, unless we have this picture of what new observables are that don't involve taking these infinities of quantum mechanics, this wouldn't make any sense. So this fantasy is only possible if we do imagine coming up with this sort of new kinematical framework that would allow us to make sense of the world finite numbers of degrees of freedom. But if there is, it's not insane that we could return to this picture. And I have some more fantasies here that I really don't have time to talk about how ultimately in the fantastical picture of the world, everything about cosmology would reduce to questions in number theory. But I will say this, that the world is filled with mysterious, enormous hierarchies. And you see, if we have a finite number, if we have a truly finite number of degrees of freedom, there's no ultimate need for the continuum. So it's logically possible that everything will turn into something number theoretic. But there's another thing which I find at least intriguing about this very wild conjecture, which is that the world is filled with these mysterious, huge hierarchies. We talked about at the very beginning, the universe is enormous compared to this tiny Planckian distances. That's something that we don't understand. The only thing that we know of out there in the world of ideas that intrinsically generates enormous numbers out of seemingly nothing are the patterns that we see in the distribution of prime numbers. Okay, so again, as part of the sort of very wild fantasy, it could be that the enormous hierarchies that we see in nature are ultimately related in in this number theory's cosmological picture to the distribution of the primes. But anyway, in this whole last 7 minutes, the idea would be that this is a possible that the Ming picture could return with a vengeance. Okay? I hope it's clear the sense in which it's true, because if it's true, knowing everything about us does tell us everything about everything. Okay? And even more remarkably so, not just unifying the few forces that we see here, but all these other crazy distinct possibilities would all actually be related in a remarkable dictionary with each other. So, and that's why we should, regardless, keep doing experiments. And people are, of course, thinking of continuing to do experiments. And people are imagining going beyond the LHC, building large colliders, perhaps 100 kilometers around, that might come after the LHC. They might blast much, much higher energies, factors of 10 higher energies than the LHC. We should keep looking for these things, these hints for the supersymmetric particles. That beautiful picture of unification is still there. The standard supersymmetric picture could be wrong. This picture of split supersymmetry, if it's right, we might miss a part of the LHC, but not by much. So it's really worth going another factor of 10 and seeing what's there. Independent of all the crap I talked about earlier in the talk, if you're an experimentalist, it's a completely obvious thing to do to follow up on the mysterious discovery of the Higgs and just see what's out there. And particle physicists love seeing pictures of the world with giant rings on them. And those pictures are starting to be made. Okay? Our friends at CERN are entertaining building a machine like this, and our friends in China are entertaining building a machine like this. And if it happens, this is something that we might have on the 20 to 40 year time scale. And it's important to look at the universe on the very largest scales. The last 20 years about looking at the pattern of the radiation left over from the Big Bang, understanding everything we can, roughly speaking about the two-point function, the simplest possible correlations between the tiny temperature variations, 1 part in 100,000 temperature variations between the temperature at different points in the sky. That's been a fantastic program. It's sort of more or less wrapping up. And the next 20 to 30 years of cosmology are all going about looking for nonlinearities, probing for nonlinearities in the pattern of temperature fluctuations. And some work that's been going on for a number of years has started showing how, in a quite precise sense, I don't have time to explain it, but really in a quite precise sense, you could use knowledge of measurements of these nonlinearities as an accelerator. The same way particle physicists use accelerators to probe for the existence of particles, we could imagine if we had incredibly high energy scales for inflation, for example, that inflation could have produced incredibly massive particles, and there are very specific, concrete imprints of the presence of those massive particles that you can look for in very characteristic oscillatory patterns in the nonlinearities that people can actually measure in the next 20 or 30 years. So both on the very short distance frontier and the largest frontier, there are experiments we can do. They can be difficult. It's going to take a lot of work, both experimentally and theoretically, to figure out how to extract the maximum amount of information from them. But looking for what the laws of our universe actually look like, right? Might not be just a parochial interest in our little pocket of the multiverse. It could still be telling us about that Ming vase, if you're listening, Mani. And it's worth doing, independent of all the motivations, independent of everything I said in the earlier part of the talk. And I think this is exciting. All right, so let me end. I certainly feel that this is a rather singular time in the development of fundamental physics. The questions that we're asking are very deep ones. It's not just is there this or that particle or this or that sort of detail that we don't understand to work out. They're very deep ones about the underpinnings of space and time, the origins and fate of our large macroscopic universe. And from a theoretical point of view, while our notion of unification is not what it was naively in the 70s and early 80s, it's developed in fascinating ways. And we're seeing increasingly deep and unexpected notions of unification uncovered in purely theoretical explorations of quantum field theory and string theory. I don't have that much time to talk about it at the end, but we really constantly have to remind ourselves, as true as all of these spectacular things are, that physics is an experimental science. And we await and need more input from experiment. If we don't pay attention to what's coming out of experimentalists, there's always the danger that we'll just, even with the best of intentions, we'll spend all day talking to our friends, impressing each other with the calculations we're doing and so on, and increasingly removed from what nature is trying to tell us. Nature is trying to tell us something nobody expected 30 years ago. And it's very important to pay attention and listen to it and think about it. And of course, it's great that we're going to have some of these experiments. Perhaps we'll have an experiment, of course, from the LHC itself, perhaps from accelerators after the LHC, cosmological observations, and there's a very interesting new frontier of even tabletop experiments that probe fundamental physics in new ways that I didn't have time to talk about. So I think it's an exhilarating time to be doing physics. You know, everyone tells you, especially when you're a graduate student, you get into physics because you care about very, very big questions, but it's a very outstanding and true advice. You have to focus on what the next questions are all the time, not just the very biggest questions, but just the next thing in front of you. And we happen to be in the fortunate state today that there are not 10 layers of questions between us and the really giant ones that sort of motivated us to get into this subject to begin with. The next steps are what are the things that are likely to be revolutionary. And all I can say is that I wish I was younger. So thanks a lot.
Thanks a lot for a very exciting talk. Are there questions for Nima?
In the spirit of Bhaumik, I just want to say that I am a local observer, and I've noticed that my consciousness expands in my own universe. And also, I had a question now. Do you think that there could be a spin 4 particle rather than a spin 3 now?
No, we have very good reasons to think you can't have anything above spin 2. That was part of this little exercise that if you give theoretical physicists enough food and graduate students, they'll figure out. If I knew what motivic category theory was, I would answer that question. So, I mean, I'll say this about it. I mean, I talked about this wonderful connection. There's been decades, centuries of wonderful connections between mathematics and physics. What I talked about here is just, one sort of a new kid on the block in this. But I would like to emphasize, it's an amazing fact about the power of this connection, that it drags someone like me into it. This is not, I'm not one of these guys. I don't know what the hell you're talking about, right? I'm not one of these guys who cared about this crap at all. It's my interest in physics that forces you to learn these things and talk to mathematicians, which turns out to be a lot of fun. But my hope is that you see, it's a great secret, is that you don't have to be very talented or smart to be a theoretical physicist. It's really true. You have to be very good friends, though, with very powerful theoretical structures who know much, much more than you about what's going on, and you have to study them and pay attention to them, and they will lead you by the nose. The really good news is they're much smarter than everyone, including these mathematicians. And my hope is that by focusing on the important physical problems, the way to think about the mathematics will be opened up in a way that's surprising to them, so that I don't have to learn what those words mean. Okay.
Okay, well, thanks a lot, Nima. Oh,
Thank you for the talk, Professor. Do you really think that space-time is four-dimensional?
Well, there's various ways that it could have substructure. One way of thinking about this idea of supersymmetry is that it's a certain kind of substructure, that there are additional directions space and time, which have the funny features that they're not measured by ordinary numbers, but by numbers that have the property that a times b is equal to minus b times a. So there are extensions of the notion of space. That's actually something interesting. This idea of supersymmetry is kind of at a halfway point between completely ordinary physics. As I told you, it's a consequence of something that can be accomplished with relativity and quantum mechanics. But the best way of thinking about it hints at an extension to our picture of space-time that makes it a little bit more quantum mechanical. And there are more boring notions of extra dimensions that I've worked on, other people have worked on, where you go to small scales and you see extra little things. It's not all that exciting conceptually. Well, it's possible. People thought, as part of the Ming vase paradigm, it is actually important that it does play a role, perhaps a negative role, in generating this vast zoo of possibilities, because you have this one underlying theory that's perfect and pristine in 10 or 11 dimensions, but there's a gargantuan number of ways of filling up the extra dimensions. So all those different possibilities correspond to different shapes for what the internal space looks like. So in that sense, they're not boring either, that they sort of lead to this huge space of possibilities.